So the first presentation is going to be covering the Python API. And this is relatively new, so I think a lot of people don't know much about it or anything at all. So we'll kind of start from the beginning. And one question that we always get is whether this is an additional purchase or a feature that you have to get. And this comes with the base Particleworks viewer license. So there's no additional configuration required. It does work on Windows and Linux. There's one caveat on Linux on the post-processing side that I'll cover again at the end, but you can't do any of the video exporting or screenshot exporting. But that's really the only difference between the two. This can always kind of trip you up. It does require a specific version of Python. So 7.0 uses version 3.8 of Python, and 7.1 requires 3.9. If you try to use it with the wrong version of Python, you'll get an error when you try to import the module. So if you're seeing a weird error, double check the version of Python you're using. And there's documentation available specifically for the SDKs. So this is in the install directory. If you go to the documentation area, then to English, unless you want to use the Japanese version, it's always an option. And then there's an SDK folder, and that'll give you the like HTML version of the documentation. And there's some example code there, and the example code that I'm showing on screen today will also make that available. So that's kind of the groundwork, but why would you actually use the API instead of just doing the manual approach? And there's quite a few different use cases for it. So the first and kind of most obvious is if you have a lot of repetitive work, and that's what we'll see with the next slide, an example of that. But if you're doing the same setup but maybe swapping out geometry, or you have to create a lot of components in different areas and you have like a spreadsheet defining those, you can use the API to quickly add everything to your scene, or quickly do a lot of post-processing, that sort of thing. The other kind of next most obvious reason would be for integration with external tools. So if you have like an optimization program, for example, or really any other tool set, internal tool set that you want to integrate your Particleworks simulations into that workflow, then by automating it out, that becomes possible. And another thing that I think is less obvious, but self-documenting workflows. So if you're trying to onboard somebody or hand off work, if you have everything defined in a script, it's in a sense self-documenting, depending on how verbose you are with variable names and comments. But it'll be very explicit what's happening versus, okay, go to this, click on this button, and then do this, and then remember to click over here. When it's all laid out in text format, that becomes easier to walk through. And then if you want to create kind of full-blown custom applications for in-house use cases, Python has graphics libraries available inside of it. So there's tkinter is kind of the default built-in one, and then there's third-party GUI libraries that you can use, so you can sort of create custom workflows with GUI interfaces and things like that. So with all of that said, I'd like to kind of highlight the different use cases by walking through this simple example. So the example itself is kind of a dummy problem that you would never actually do, but I think it highlights some of the reasons that you would use the API. So in this application, we have basically a tank of fluid that's angled out, and as it spins around, fluid is going to go up these walls and then escape out of these portholes. And what we want to do is measure how much fluid is coming out of each hole, and we only want to run the simulation as long as it takes to sort of converge on that number. So the first problem that we run into is if we want to measure the flow rate at each of these holes, there's a couple of different ways you can do it, either as a post-processing step or by using an outflow and then reading the outflow result data. But in either case, we're going to need to create a lot of different objects at each of these holes, right? So because we made this in CAD, we know where each of the holes is, and that's pretty easy to do programmatically. So we can just sort of create a simple loop that creates all of these and positions them. So that's what we see over here in this relatively simple script. Most of the lines here are just assigning positions. So all this is doing is going through, it finds this this housing here, this container. That's the ASM 009. And we'll use that because we're going to parent all of these objects to that housing so they spin together. And then it's going to go through a loop going around the circle and then going up and down. So there's two different kind of levels for each of these holes. And then for each one, it's just going to position them, set the circular height or circular diameter, basically. And then it'll attach it to an inflow that we create on the inside here so that we just have a closed loop of fluid. And that's really all that we have to do. So instead of clicking and dragging and making sure everything is in the correct spot, we can just do this. And if we needed to change anything later on, it becomes pretty easy to either programmatically or in the GUI delete everything and then recreate it with, maybe a different angle positioning or different heights or anything like that. So then we've already set up everything. And the next thing we want to do is dynamically monitor the simulation as it's running. So for the sake of this example, I'm running the simulation until a certain amount of fluid has escaped through those holes. But we could sub in any complex logic we want here. And that's kind of the advantage, that instead of running a simulation all night when in reality we got the result we needed in 4 hours, we can have the software every couple of seconds or every couple of minutes check some result parameter and say, I have achieved my target, or I haven't achieved my target, or this simulation has failed for whatever reason. I can stop it. Failed in the sense of this design isn't working, for example. So in this case, the example I'm using, it's using a pandas library, and you'll see this in the full code. But on each of those outflows, there's an outflow dash name of the object. And that's a CSV file that gets kicked out whenever fluid is escaping an outflow. So by using code, we can parse through all of those every couple of seconds and then add up the total amount of fluid being that has come out of those holes. And once we achieve some target, then we can stop the simulation. If we wanted to do something more complex, like wait until over some period of time the result has converged to some level, that's completely possible as well. That's actually on the GPU benchmarking script that we have. That's actually what it's doing, is looking for some convergence in the time per time set. Okay, and then the last example I want to go through is post-processing. So a lot of times we have a bunch of different scenes where there's just minor modifications, and we want to run the same post-processing for all of them. Sometimes it becomes too tedious, so we end up doing sort of a lesser version of that, manually inspecting what's going on. But if we can create a standard script and then run that for each simulation, once we've run the simulation, then we can get a lot more useful information with a lot less work. So in this example, what we're doing is creating a video, then adding a surface object, or creating a surface object, and then generating another video with that. And then we can also pull out information from the text output. So there's like the torque values that we could be looking at, or the outflow, which is what we have here. And then summarize all of those, because a lot of times, there's 20 columns in all of those spreadsheets, and we only care about one of them, or maybe even just a couple of rows and a few columns. So we can pull all of those out automatically and create a single summary with all of the information we want. And then, like I had mentioned, the video and screenshotting isn't supported on Linux. There's some library limitation there, but everything else we can do on either Linux. So if you're running on a remote cluster, you could have a workflow where you pass it some Python script to run when it's done, or maybe you pull the data back to your local machine and run the scripts there. Okay, and as you're getting started with these, we can always help you, kind of getting started and debugging code and things like that. So don't hesitate to reach out.